I start my recording. The other recording is in progress. I created a new Teams group. It's very weird that there is no Teams group for this lecture automatically. Can you hear me? Are you there?
Yes.
Okay, thank you very much. Great. So I'm still here. I have 3 screens, one on the notebook, one there, and the presentation is there. That's why I'm looking there. But I switch off my camera so you will not see me. Okay, so let's start. This is the last lecture, and then you will write the midterm test and the retake of the midterm test. I hope that's the best for all of us. At least you will have a grade at the end of the semester. The semester was unusually short, so if I just check this out, we had 1, 2, 3 lecture in November, and 1, 2, 3 in October. So that's 7, and there were some other lectures, so it's altogether 11. Let's check. The last talk was the presentation of the last talk had poor quality. I use AI to take the original Hungarian text and the images from the slides that already had done. I also improve a little bit the slides and change the text from Hungarian to English on the slides. But last time the ChatGPT was not on the top, so there were a lot of problems, so I will repeat what I had taught. Not everything, but most of them. There are new things that's very interesting about lasers. And there are some problems. Here are the topics, that's the official. We will talk about this luminescence, phosphorescence lasers. But I have no time to talk about this basic knowledge of nuclear physics and particle physics. Honestly, I have no clue what is in this topic, but I have imagination, so these are the topic. I will provide you a video or some links and so on. You will deal it. Of course, I will not ask, I will not claim this knowledge at test and midterm test. But it would be nice to check this out, because this is some type of your legacy or something that you gain from this talk. I sacrifice this for the better good. This is about nuclear physics, but I had no clue what I should tell you about particle physics. Something was given to you, but well, there will be a lot of work to describe everything properly. Okay, there are other problems with the practice. Okay, this will be the luminescence, fluorescence, phosphorescence and everything, but let's go back time, 2 weeks. I hope you enjoyed your holiday. I have no clue why was this holiday last week. Everyone had in the last week of October, so that's a bit weird. Wait, I got a message. Oh, welcome. Okay, so let's return to the original stuff. So this is luminescence, and the new shiny slides of the previous talk. Okay, so that was 2 weeks ago. I talked about a lot of things. Thermodynamic phenomena, magnetic properties, ferroelectricity, piezoelectricity, electrostatic, liquid crystal, superconductivity. That's a big chunk. I should have tell less. So I think that part with the volta batteries and contact potential was quite good. I will not repeat it. That was good. That's okay. I added some details here. You can check in the slides. But okay, the magnetic properties of solids, dia, para, and ferromagnetism. Okay, I told you that the electrons rotating around the core, and this gives us magnetic property, magnetization, the magnetic moment per unit volume. That's the magnetization. If there is matter, we are not in the vacuum, then we have to change the magnetic field. It's different then. This is the magnetic field in vacuum. There is a special constant that modify the magnetic field. Actually, this constant is not constant. It's a tensor because these are vectors, but doesn't matter. So if you write down the magnetic field in this way, and you go through this calculation, you can introduce this property, this kappa. This is called magnetic susceptibility, and this is very useful because depending of the value of this kappa, you can classify the materials. If this is small and this is around 1, then if you put a small magnet from this material to magnetic field, then it turns oppositely to the magnetic field. This is called diamagnetic material. If you have these restrictions for kappa, then the same magnet are not the same. For the same, the similar magnet from that material turns parallelly to the magnetic field. If you have a large kappa, then it depends on the magnetic field strength, then the behavior is like last time, just we call this ferromagnetic material. What can we do? A lot of things, but I have to explain this hysteresis curve. This hysteresis is the following. This part, this is the magnetic field, this is the what, just a moment. Okay, so the proper name of this H is magnetic field strength, and this is this B is magnetic field density. Doesn't matter. So you have this diagram. You start from 0, add magnetic field, then there is a virgin or initial curve when the material reaches this point. Then if you reduce the external magnetic field to 0, the magnetic induction still remains in the material. That's called remnant induction. You have 0B, but you have magnetic induction here. That's 2 is that one. If you increase the external magnetic field in negative direction, then you can reach the magnetic field, I mean the magnetic induction in the material, to 0. There is something. The value of the external field strength at which the magnetic induction in the material becomes 0 is called coercive field strength or coercive force. That's it. If you're increasing the field in negative direction, that approach the negative saturation. So this point that we reach this point because the material has its own features and allows to reach this point. But in the other direction we can reach this again. Then we go and increase the magnetic field from negative to positive, then we go through on this curve. And it is again negative, I mean the induction becomes 0, and then you return for this. So you will go around this. This curve is important because that's the virgin curve, but this coercive force is also important. This green area is very important because this corresponds to the work required for saturation. If the area is small, then we have a soft magnet, otherwise we have a hard magnet. Materials with high coercive force and high remnants are suitable for use as permanent magnets. If the temperature increases, the ferromagnetic material eventually becomes paramagnetic. There is a point, a temperature, that's the lowest temperature at which a ferromagnetic material becomes paramagnetic. This was important. Last time I talked about the moving of plates and a lot of things. So for example, when a volcanic material comes and cools down, then after a while it will be ferromagnetic, not properly, but there will be some feature. And when it reaches its Curie point, and then the magnetic field direction at the time when it reaches the temperature, the surface, or it cools down, then it is frozen in the magnetic field. This is good for sometimes to determine the time when this frozen was, but when the time is determined somehow, then you can determine the magnetic field direction. Okay, if you go to a transformer, then I told this, you can hear this strange noise. This is because the magnetic field changed the volume of the material. This gives the sound. Okay, let's jump to electricity. The electricity has same features like the magneticity. There is also a hysteresis curve, and there are dielectrics and lot of things, and this similar feature to the ferromagnetism is called ferroelectricity. If you have a ferroelectric crystal, that's good. If you add external magnetic field, then it has also a Virgin curve. It also have a point when it reaches the zero, when the external field is zero, but the field inside the displacement vector is not zero. So you can do the same, more or less. This is big, so I don't have my books here, but I learned not from this soft and beginner level of book that you have this Feynman, but I use the Landau series, and this part of this electricity and the electricity in magnets and magnetic field in materials, electricity in materials and magnetic field in materials, displacement vector, and so on. Well, this is a few thousand pages. I didn't learn everything, but to understand this properly, I would need more time, much more, semesters. So not just a few minutes. What you can use, and I mentioned this piezoelectricity. If you push or pull a crystal, an appropriate crystal, then you can experience some electricity, and it's good in lighters, but you didn't know it last time. I was a bit disappointed. Or gas igniters, or something like this. This is a way how you can you use electricity for everything. So for rule things and conduct things, but sometimes you have to move things. Sometimes you need a light. Sometimes you need something. And then this piezoelectricity can help you. There were magnetostriction, but there is electrostriction. If you have electric field in some crystal, then it could be deformed, stretched, compressed. It was discovered by Pierre Curie. The electrostriction is the inverse of piezoelectricity, and it helps. The magnetic field follows. The electric field changes, and the structure of the crystal reorganized and the volume changes. This is good in quartz clocks, diesel injectors, and so on. So this is a useful feature. Okay, this was very poorly explained last time. Liquid crystals. Sorry. So in liquid crystals, these are very, very important. Very, very important. My screen, your cell phone screen, your clock screen, the displays, everything is based on this liquid crystals. Just a moment, I have to throw down this tissue. Okay, I returned. So what are these? When I talk about liquid crystals, I suppose that you have some preliminary knowledge, but well, perhaps I accept too much. There were this guy, Austrian botanist. Oh, in the first time he was Austrian-Hungarian, but doesn't matter. He had experience with cholesterol benzoate in 1888. It's a crystal. He started heating, and it heated to 145 Celsius degree. Then he got a cloudy opaque liquid. He heated more, then it became clear, and it became a transparent liquid. This material has two melting points. That's quite interesting. Lehmann made further studies, and he determined that this cloudy opaque phase has optically anisotropic regions. I mean, there are threads, longer regions in this state, and he baptized this state liquid crystalline state. Someone lost the internet connection, I guess. In 1968, this other guy suggested that liquid crystals as materials are suitable for microelectronics. This is a new state of matter. There is solid, liquid, gas, plasma, my field, and liquid crystal. Actually, I call the fifth state of matter the super liquid helium, for example, but doesn't matter. So this is a new state of matter. It's macroscopically liquid, microscopically like a solid stuff. There are categorization of these liquid crystals. One, the ordering of the centers of mass is preserved, but orientational disorder is present. The other, ordering of the centers of mass disappears, but orientation order remains. So by definition, liquid crystals are materials in which the complete simultaneous ordering of molecular centers of mass and molecular axis does not occur. There are groups of liquid crystals: thermotropic, formed from crystalline state upon heating; liotropic, formed from crystalline state in a presence of a solvent. This is more common in living bodies you can find this. Okay, this was extremely skipped last time. The classification of liquid crystals. There is this smectic. There is a layered structure. In the molecules in the layers oriented randomly. The layers can slide over each other, and this is thermotropic. I mean, comes from a melted crystal. Nematic. Molecules form a thread-line chains like this one. It's different than this one. The axes are parallel, but they do not form layers. Toothpick model. That's the name. I don't know whether this term is good in English. I hope so. Cholesteric. There is a layered structure. In each layer, molecular axes are parallel. In different layers, the molecular axes point in different direction. That is a periodic rotation. They rotate the polarization of light. That's not bad. So this polarization of light is something good. It's something useful. If you have two, for example, perpendicular direction for polarization of light, then you can switch on and off light, for example. Cholesteric. There is also layer up. What happened here? Okay, it seems I have to remove one slide. No problem. Later. What is the importance of this liquid crystal displays? Liquid crystal, that's the most important. There are two different ways. It's too difficult to explain. You have light from here. The light is passing, and there is a polarizer, there is a glass, there is an electrode, there is an orienting layer, liquid crystal, orienting layer, again electrode, glass, polarizer. The other, then you have this direction incident light, and then there is reflected light, and this is the structure. Doesn't matter which is important. You have, and also have to give you this LCD displays. That's liquid crystal. The definition of this LCD later. The liquid crystals are there, and if you have this, then you can rotate the polarization of the light. Well, I don't see your face, but in theory you should know what is polarization. The direction of the waves is this. They are turns here, and then you have a light. I mean, not there will be a light, that's something else, that's the system of Maxwellian equations. But there is something. If you do not change the direction of the polarization of the light, just try to pass, and you have a polarization filter in this direction, and there is this direction. If you change the direction, then you have light. If you do not change that, you have a dark display. This is how LCD works. Well, this is why you should listen to this, because that will be useful later. Okay, most interesting stuff. Superconductivity. I have seen it. If you decrease the temperature, then you reach zero conductivity, infinity conductivity below certain degree temperature. You need poor metal, for example mercury, Otherwise you will not see this, and there will be residual resistance at 0 Kelvin. You cannot reach 0 Kelvin, but you can reach very, very close nowadays. In that days, if you had 1 or 2 Kelvin, that was nice. So this was what this guy, this Kamerlich, Ons, I don't know the pronunciation of Dutch physicist, find. The mercury lost the resistivity at 4.2 Kelvin. The aluminium needs this one. The tin, this is the tin, needs 3.7. This critical temperature is important. The temperature at which the electrical resistance of material falls to 0 is called critical temperature. Those materials which has this temperature are the superconductors. These are the first type superconductors. These are pure metallic superconductors. Copper, silver, and gold cannot be brought into superconductive state. What are the advantage of this? If you don't have resistance and you put some electric current in a ring and you keep the temperature, you have the electricity in the ring for 1,000 years. And if you want to transfer electricity, you don't need big wires and everything. Without any loss, any heat loss, you can do it. The problem is the low temperature, but not only the low temperature. For mercury, the low temperature is one thing, but also the magnetic field is important. If it's too high, there is no superconductivity, and also with high electricity, you don't have superconductivity. In 3 dimension, you have electricity, you have magnetic field, you have the temperature, and you have this corner in this 3D diagram. And in this corner, the lead, the lanthanum, mercury, aluminium, zinc, uranium became, check the uranium, it's interesting, it's very low, became superconductive. But for us, I mean for economic reasons, we cannot use this. For example, alone this low temperature can be reached by liquid helium. The helium is the second more frequently material in the universe, but not in the Earth. There are some natural source. We are living on a rock planet, and at Jupiter and Uranus or Saturn or Neptune, it would be much more easier to find helium, but here that's it, very, very, very expensive. Additionally, the isolation is horrible. In that temperature you have humidity and it is frozen, you know very well. So it would be nice to reach higher temperature. Fortunately, not poor metals, but some metals, alloys, this is a mixture of metals, and some ceramic materials became superconductive higher temperature. If you check, this is much higher, and this is called type 2 superconductors. Why? Because these, not the alloys but the ceramics, are poor conductors. If I scroll down, then you can see with special ceramics you can reach high temperature. You cannot see my hands. This is much higher than the previous one. So you need liquid nitrogen to maintain this temperature. So the experiments are much cheaper and everything is much cheaper. This is economically useful, but the best would be that if we had superconductive material at room temperature. Then it would be easy to store electricity, it would be easy to conduct electricity. That would be very, very nice, I think. I hope you can hear me because I see the mic a little bit shifted. Okay, the most important, very interesting stuff. Until certain magnetic field magnitude and below the critical temperature, the superconductive material expels the magnetic field from the interior. This looks like nice here. If you have this superconductive material, liquid nitrogen, and put a magnet on it, it will be levitated. This is not this one, but this would be a magnetic levitation. You can build railways in this way. This is nice. I have seen it and made experience with it a long time ago, really long time ago. Actually, it was 42 years ago. Additional stuff. Why are these material become superconductive? The materials has a strange feature. If you multiply the critical temperature and the atomic mass, you got a constant amount. This indicates that this superconductivity is, and the conductivity is related with the vibration of the atoms in crystals. This vibration can be considered as particles. We called them phonons, not photons, phonons. The phone and the photon gives this the term. So the superconductive state, the electrons form bond pairs. These called Cooper pairs. And these pairs are not permanent. They break and recombine. These pairs has half and half together. Half minus half is 0, and then these pairs behaves as particles. I explain you what is the Fermi direct statistic that gives the resistance of the metals and materials, but the Fermi direct statistics are fermions, which has half spin or minus half spin. This has 0 spin, so this is not obeys to the Fermi direct statistic. It obeys to the Bose-Einstein statistic. So it crosses through energy levels and everything and the materials. If the electric field is applied, the Cooper pairs accelerate collectively, and some energy is required to form Cooper pairs, and this binding energy lowers the Fermi energy of the material, and the forbidden energy gap opens above a Fermi level in the band structure. So we have superconductivity. There is other stuff. If you have a superconductor and you have an insulator layer, then the Cooper pairs would pass. This guy still live, I hope so. As a young university student, discovered this phenomenon. So with tunnel effect, quantum tunneling helps these pairs to cross this insulator. This gave this guy Nobel Prize. Also, these guys got Nobel Prize. So we are in this. Something is not in the material, but I told you there is something special and only discovered with the helium. After a while, when you reach very low temperature, the helium became superconductive. It means it looks like it does not have viscosity. Actually it have, but if you have helium in this place in an open tank, then it will reach the wall of the tank and then leaves the tank on the surface of everything, and then it collects in the lowest point of the closed room. Of course, it will boil or everything. The only matter that shows this feature is the helium. It has a very special explanation, but it is suspected in the neutron stars. This is one final state of dying stars. Also, there is super liquid fluid in the middle. Okay, this was the material of the last course. Sorry, I will upload everything and also upload this movie and everything in time, and also the exercises that we have. So let's switch to the today's stuff and the last thing. Luminescence, fluorescence, phosphorescence. You must know this. I look into your eyes. You must know fluorescence and phosphorescence, because on the pointer of a clock, an old clock, or many materials you have this. But what is this? What is the physics behind it? The luminescence is the emission of visible light by certain materials when exposed to visible light, X-rays, or radioactive radiation. Unlike thermal radiation, this emission occurs even at low temperatures. So it's something different than thermal radiation. I started the lecture with that one. Luminescence, the emission of light in cases where the origin of the emitted radiation is not the temperature of the emitting body. So it's called luminescence. Materials that emit such radiation are referred as phosphors. The mechanisms including luminescence. There is light, then it's photoluminescence. Electrical phenomena, and you have light. Electroluminescence, actually this is here a bullshit. The Cherenkov radiation is not electroluminescence. I will delete this. This is stupidness. The Cherenkov radiation is that when you have radioactive particles, for example at nuclear reactors, when the speed of the particles are higher than the speed of the light in the material. It's not higher than the speed of light in vacuum, but in the material it's higher. So you have a very similar feature like sound, like supersonic stuff, and this sonic bang. That's the Cherenkov radiation. Radioactive radiation, radioluminescence, biological processes, bioluminescence. These are fireflies and certain bacteria has it. Luminescence occurs when material absorbs incoming radiation and subsequently re-emits it, typically at different wavelengths. That's important. Typically, the emission is at different wavelength. That's use of a practical application of this. Oh no, this feature. Duration of luminescence. The time interval during which a material continues to emit light after the excitation is called luminescence lifetime. Luminescent versus non-luminescent materials. Poor crystals with few defects do not luminescence. The crystal defects are required for luminance to occur. The impurities often enhance the effect. Impurities that facilitate the process called activators. Phosphors, that's not that phosphor. The base material is Jesus Christ, zinc, sulfur, barium sulfur, cadmium sulfur, barium chloride, natrium chloride, sodium, not natrium, sodium chloride, and activator that's silver, copper, bismuth, mangan, and telluride. I hope that's the English term too, not the Hungarian. How it looks like. The fluorescence is the form of luminescence when the emission ceases almost immediately after the acceleration stops. There is only a microseconds. The light emission effectively ends as soon as the acceleration is removed. So what is, sorry for the Hungarian text. So these are the Valencia belt lane. There is the energy level of the activator. I mean the silver or other stuff. And this is a conductor lane. You have a photon with this energy. You put this to from this activator level to this conduction level. And then, after a while, it emits another photon. First photon jumped from activator level to this leading level, moving freely, and meet another activator atom. And then there is a recombination. Okay, so this is fluorescence. Phosphorescence is very similar. Luminescence, even though I knew it in primary school, occurs when there is light. When the light is continued, so the emission is longer, the luminescence in which emission persists for a significantly longer duration, it's called phosphorescence. Some minutes could be, but it could be some hours after the acceleration ceases. A recombination inhibiting mechanism must be present. So there should be some process that keeps this radiation longer. There are traps which traps the, what is the name? The materials, it's the electrons in crystal. Blah 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 blah. So it lasts longer. There is a deduction. The Stokes, actually, you know, Navier, Stokes equation, Stokes integral form, and a lot of things you know from this guy. The frequency of the fluorescence light cannot exceed, and its wavelength cannot be shortened than the frequency of wavelength of the exciting radiation. So the frequency you shall not pass. Okay, so this was of course bound after the bar of Memoria and not related to your grades. So you have a radiation, something, and what you got in fluorescence or phosphorescence or everything is something different, and this is longer, so the frequency is lower than the original wavelength. You have the incoming photon, great, it has some work to do its job. The emitted photon has this, and this is the work that you need for this emission. Of course, you have this one. If you divide with the Planck constant, you got this. So if you use this stuff, I mean the equation, you can write this, change everything, reorganize, you got this one. So the wavelength of the emitted photon is higher than the original one. We wanted to prove this one. Great. Application of phosphorescence. Wavelength conversion. So you have problems sometimes the light. For example, if you have lamps, that lamps uses mercury, the light will be a very ugly blue, and some UV radiation will be. But if you have some fluorescence stuff in the lamp, then you can shift the wavelength with it. Also, you can use it in CRT television scripts, oscilloscope screens, clock dials, and so on. So the application is infinity. Okay, we are very close to the end. The end is near, but we will have much to do. Well, lasers. I will teach you what is laser. Sorry for the Hungarian text again, but you can understand something. You have a photon, and the photon enters to an atom. And the atom's electron or electrons switch to a higher energy. We call this absorption. When there is an electron higher energy and jump to a lower energy, then a photon appears, and the excited electron jump back to the normal basic states. We call this spontaneous emission. So there is absorption when photon enters and increase the energy level of an electron, and the opposite is the spontaneous emission. Okay, let's jump. There could be a very interesting stuff. It's called popular inversion. Then more electrons are on the higher state than the lower energy. That's very weird because the energy consumption and the principle of the energy minimization suggests to have electrons here, at least more electrons here than here. There should be something, a photon, that stimulates this stuff and maintains, but this situation is very weird when you have more electron on the excited level than in the basic level. We call this population inversion. That will be very important. Okay, I return to you. So we had absorption, spontaneous emission, and population inversion. Okay, we have spontaneous emission because there is induced or stimulated emission. We have photons, we have many electrons on X-side level, perhaps we have a population inversion, and it emits photons. It's called simulated emission, but stimulated. These photons have identical wavelength, and the phase of the waves are the same. So we have a bunch of photons which has identical in wavelength and coherent, the phases are in the same. Now we know everything to create masers. Maser means microwave application by stimulated emission of radiation. Devices that amplify microwaves through simulated emissions and subsequently emit microwave radiation called masers. I will answer you later what is it. This maser is in microwave, and in the nature they are more frequently than lasers. Lasers and masers exist in the nature too, as well as nuclear nuclear reactors. There are some nuclear reactors in the Earth. There were actually, but doesn't matter. Which is important? This laser. Devices that amplifying light through stimulated emission and emit coherent light waves are called lasers. The first maser was built in the 50s, and the first laser, it was a Rabi laser, was constructed in the 60s. This stimulated addiction was predicted to Einstein, so praised be Einstein gave us this laser too. He was the superstar of the science actually. Now I explain you the lasers and why they are so important. Sorry for the Hungarian text again. What we have? There is no two-level laser. There is a basic level, there is a pumping energy, and then spontaneously jumps to a level, and from that level with stimulated emission we does some stimulated radiation. These photons will be coherent and in the same wavelength. And now the top of the semester. This is the laser. The laser is something same, but you are more familiar in laser. There are a medium, matter, and the atoms are in the ground state, basic state. This is a tube actually. It could be a ruby crystal, it could be carbon dioxide, it could be a lot of things. From this direction, so the perpendicular to the axis of the tube, we excite. We pumping light, and this excite most atoms and ions in higher energy state. These are the anticycles. The ground state means this full solid cycles. The excite atoms spontaneously emit photons along the resonator axis. Actually, not along the resonator axis, but everywhere they emit. But we have a mirror here and a semi-transparent mirror here. So these photons, which moves parallelly to the axis of the tube, bounce back and also got more energy from the excite atoms, and these photons stimulates emissions, so they gain more photons and travels to the mirror. From the mirror, the bounce back gains more energy, and they can leave this stuff, or they can bounce back a few hundred times or whatever. Finally, photons with the same wavelength and with the same phase appears here, and that's the laser. This laser is very, very useful. Of course, not for Star Wars, but now we have a very good weapons with this. It's very useful against drones and anything that flies slowly. With rockets, to get them is very, very expensive. Machine gun can help, but if something can change the direction and the speed quickly, then the machine guns cannot follow them, then laser guns can help. But if you are not aggressive and not in the military, you can use laser pointer, or you can create a lot of things with laser. One is the 3D pictures, the holograms. Let's check this. This is, sorry for the Hungarian text, the helium neon laser. There is gas, helium neon. Well, the helium is rare and expensive, neon is not so expensive. So we can use this. This is the full reflexive mirror. This is a semi-transparent mirror, and that described here, this normal state, excitement, some of them bounce back, and stimulated emission helps, and then stimulated emission again, and after a while we have lasers, is going here. The excitement, I don't know, perhaps that's radio waves, I don't know, I'm not familiar with this. You are more familiar with semiconductor lasers. That's the cheapest. You have a P and N type polluted semiconductor here, and you can get coherent photons, lasers in the same wavelength. That's called laser. This is the cheaper stuff, and in LED bulbs, in this horrible white blue reflectors of the cars, and actually in my bike's lamp too, we have these semiconductor lasers. The only way how to produce energy is this one. There were a significant, there was a problem with it, because originally we got green and red light, and that was not useful. A Japanese guy, and actually 3 Japanese guy got Nobel Prize to create these light blue lasers, and that guys got Nobel Prize, which is very funny. The researcher's life is very hard. Usually you are in a temporary job. I have a blog, but it is in Hungarian. Actually, the structure of the science is very similar to drug mafia or crime corporations. Doesn't matter. So from one had to leave the science and move to the industry, and Nobel Prize was not enough to get permanent job. That was funny. That was a few years ago, 5, 10, I don't remember exactly. Other stuff, this Rubin, that's the original laser. This is the Ruby. This is the mirror. This is the semi-transparent mirror. And this is a flashing lamp for the optical pumping. And this is the laser. But this is the Ruby laser. This is more important. This is something Hungarian. No, actually, he's British. Denis Gabor. Yeah, so he also worked and got Nobel Prize for this hologram in the UK. Well, we have a lot of Nobel Prizes, at least we Hungarians say that, but most of them worked outside of the boundaries of Hungary, so they are considered German, French, English, British stuff like Denis Gabor, Eugen Wigner, and Leo Szilard. So these are typical English names actually, but we have 2 Nobel Prize winner, novelist, and 1 biologist, Albert Szent-Györgyi. These are considered Hungarian Nobel Prizes outside of Hungary, doesn't matter. Which is important. We have a laser, we have the subject, and we have 2 mirrors, and we have this film, I mean the record stuff. This pattern creates the lasers. You need laser for this because you need coherent radiation with one wavelength. So the lasers creates a pattern, an interference pattern, and this interference pattern is recorded in the film, and this is reproduced by normal light. Actually, it's possible, and That pattern is the 3D picture, the hologram. And this is the end. This is the end of the theory and everything. So now I need a few minutes break, 5 or 10 or something like this, and then we switch to practice. So thank you very much. I stop this recording, my recording, and continue 5 minutes later. Thank you.